Okay, so the session is about AI networking. I don't know if people here have heard about AI networking recently. Show of hands, just one person, two. Wow, you guys are really missing out. So what this talk is going to be about is 3 sections, and it's going to be presented by 3 people, surprisingly. I'm going to cover the essence of networking and AI and why the two intersect. So I'm going to go over some very basic ideas of what is happening and why is networking for AI different from what other solutions and other attempts in the past look like. And I've strategically put some errors in the way I'm presenting things. So please pay attention and find them and see if you can engage with us that way. Then Nick is going to talk about some kernel patches that were sent recently. This is the introduction of this new technology called UET, Ultra Ethernet Transport, which is a product of the Ultra Ethernet Consortium, which is a collection of 140 plus companies that is trying to revolutionize the way high performance computing, especially in the context of Ethernet, will look in the next few decades, I hope. And then Costin is going to cover some very interesting work that they did about how machine learning networks actually behave in the wild and the kinds of problems they face and the solutions that could be applicable. Okay, so without further ado, let's talk about how these systems work. So what you see, the picture that you see on the left is, you can call it a cartoon representation of how systems that are trying to do machine learning look like today. And if you notice, the first thing that you should notice is there are 3 fabrics in this system. There's a PCI fabric, there's a green Ethernet fabric, and there's a blue, what we call IPC and cloud native fabric. All these things have to communicate with each other at max speed and at max efficiency. Now, this kind of network looks different from what any other network that you would see in a hyperscaler that has been very popular for the last 2 decades. Because hyperscaler networks, if you notice, were built to be resilient. They were built such that you could build 1 million, 2 million endpoints, and they would provide a lot of aggregate bandwidth, but no single endpoint was trying to be able to use all of the bandwidth all the time without failing. In fact, failure is built into the system. A machine learning network, which would comprise of millions of endpoints that look like this, is trying to build a single fault domain and aggregate all the bandwidth at the same time, which is an interesting problem to try to solve. So what is being communicated? What is actually happening? And that's the part that I want to focus on today, right? So if you look at this picture, the classic neural network, what it's showing is a bunch of vectors that are being transformed. And the way they are being transformed is what is shown by the boxes below, which are basically 2-dimensional matrices. So if you look at the X and the W, they are being multiplied to get the H. The H and the W are being multiplied to get the O, and so on and so forth. And in the next few slides, you'll understand what that means, I hope. Oh, I don't know if I warned you guys, there's going to be math. So matrix mathematics, right? So for everybody who's forgotten this successfully, I'm sorry, I'm going to bring this back up again. So if you look at this matrix, it's actually talking about 2 matrices, A and B, and they're being multiplied. And the way they get multiplied is what's shown, right? The 1 and the 2 gets multiplied with the 6 and the 8 in this particular way, and then you get the result 22 in the top right column. What is interesting is this matrix multiplication can be sharded. Now, if you combine this with the slide that I was showing you earlier where 2 matrices are being multiplied, what you can understand now is that if these matrices get really large, you can shard them and you can distribute them. If you shard and distribute them, then what you have to do is you have to collect the result, because now what you're going to get, every one of these shards here is going to give you a partial result. And then you have to add them up, as shown by this addition sign here, to get to the final result at a particular row and column. This is the essence of what the problem with machine learning is. A very common and popular rule or system that is used for doing this kind of matrix sharding and reaccumulation is called scatter reduce, which is then followed by an all gather operation. And we'll talk about that in a second. But before we get there, to be able to solve these really large, complex matrix multiply operations, there are a couple of ways in which people have tried to do this. The two most popular are a ring or a mesh topology. A ring topology is a bit more efficient in terms of total number of links needed. A mesh topology is significantly faster, but requires a lot more ports and a lot more links. Convert that into a lot more cost. So I'll not go into the detail for that right now, but let's suffice it to say a ring is what most people implement and deploy today. It turns out you can build that logical ring of the previous slide using a system like this. So if you imagine a story where you have 4 nodes and 2 switches, you have a red ring and a blue ring, right? And the dashed line is the return path of the ring, which is shown for completeness. So essentially, it's this picture implemented this way, such that you can have this concept of a logical ring. Now, why does that matter? Hopefully, you've heard the term all-reduce before, or as I call it, the almighty reduce. And the reason why all-reduce matters, if you scroll back all the way to this slide, is this. This is the reduce operation, right? So you're doing a bunch of multiplies and then reducing the result to get to that final sum. And a way in which this could work is imagine you had 4 nodes in that ring, and imagine you had 4 vectors, A, B, C, and D. The way you would solve this problem, which is a reduction across the board, is by doing, let's say at step 1, A0 gets sent to node 2. B1 gets sent to node 3, C2 gets sent to node 4, and, C2 gets sent to node 4, and D3 gets sent to node 1. So you can see now, node 1 at the end of this step has A3 and D3. It has added those two. Node 2 has A0 and B0. Node 3 has B1 and C1, and so on and so forth. So far, so good? Next step, note the ones that were added. That's what you will send along. So we sent A3 and D3 along. We sent A0 and B0 along, blah, 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 blah. Now you can see the partial sums are building up. And the next step, voila. Each node has one partial sum. Now all I need is a broadcast operation and everybody's happy. So if you put all the pieces together, you have a matrix. You can do sharded matrix operations. You can find the final result by doing a distributed reduce. And you can do such a distributed reduce on a ring in a fairly efficient manner. This, in a very, very simple sense, is the essence of machine learning. Now, how do you get that? So I'll give you an example. This is actually an inference case, not a training case, but whatever. And the picture is a little hard to see, I suspect. It's on purpose. What it's talking about is an LLM model of this sentence: data visualization empowers users to, and an inference engine effectively predicting the next word, the next token. And what it's doing is it's effectively multiplying this, a vectorized version of this sentence with itself. You can't see it, but each one of these are a replica of this exact sentence. And it's using a model to figure out how important that cross product, the self-attention, so to say, looks like. And you can't see that here either. There's actually 12 different models that are being used at the same time. Each one is what's called an attention head. Then it goes and does a sparsification and then a densification to scale the appropriate interest levels. We won't get into that math. You can breathe easy. But what is worth noting is every one of these are an instance of that matrix multiply operation I was talking about earlier. And if each one of these matrices was 1 gigabyte or 10 gigabytes in size, you can see how that sharded matrix operation is going to get very complicated. And all these different sub-matrix operations have to be reduced to get to the final result. This is being done 50,000, 100,000 times per second, per model, per user, and so on and so forth. That's the reason why machine learning has become such a big problem. The other part of this problem, right? Remember what we said earlier, that what you're trying to build here is effectively a distributed supercomputer, but it has all the sensibilities of a supercomputer of yesterday. So you get all the benefits, the theory at least is, you get all the benefits of building distributed systems, but you get all the value of a supercomputer. And that's really hard to do. So if you look at this picture, this is what any large data center internal network topology will look like. But there's a problem with this. This system was built such that you could say any one of the node zeros or ones could fail, and your system would survive. But it wasn't built for the case where node 0 and 1 have to always be up, and they have to always be able to communicate at max bandwidth, and there will be no congestion in the spine, and there will be no congestion in the leaf. So the machine learning version of this network looks like this. Anybody not see why this is interesting? It's okay to say. All right, well, if it's already obvious, I'll just state it for effect. What you've done now is effectively created these things called rail switches, where every node 0 can talk to each other. And as long as within the node 0 set, you know that who's communicating and who's listening, then there will never be congestion, and the rail will always be sufficient for you to get to your destinations. The spines are only there for the overflow case, or for the case where two transactions overlapped in very, very bad ways or slightly bad ways. Anyway, so now if you look at this story, you understand what we are going to talk about next, which is one of the problems or one of the reasons why UEC exists, which is to try to build these class of networks, not need to build this class of network, and be able to provide all the requirements on Ethernet of a highly capable infrastructure that is going to deliver full link bandwidth at a very resilient point and with the kind of efficiency that is required for these kinds of distributed computing systems. Okay, so we'll take a short right turn and talk a little bit about UEC, and then I'm going to let Nick come and talk about what we are doing for it, or what the Ultra Ethernet Consortium is doing for it, and the efforts we're taking in Linux. The first is, like I said earlier, this consortium has 140 members. I think it's 140. Somebody fact check me on that. It's a lot. And it's sort of a universal understanding that Ethernet is going to be the long-term system bus for these kinds of large-scale distributed systems, and fundamentally come up with the technologies and the tools that are required to be able to build, maintain, manage these kinds of distributed networks. It has a lot of functional blocks. The consortium is looking at everything from link layer issues, physical layer issues, transport layer issues, software layer issues. It has a group looking at storage, a group looking at compliance, a group looking at management, et cetera, et cetera. Today, for the rest of this session, we're going to focus mostly on the transport and the software implementation of that transport, which is what's marked out. The overall stack up looks a bit like this, right? So the application interface of choice is going to be libfabric. So the bottom end of this API is going to be completely plugged into libfabric natively. It's got all the libfabric objects and object representations that it needs, such that you can look like a native libfabric provider. And underneath that, you have the vendor UET provider, which has all of the standard components that you can imagine: control, communication, completion, and the actual data transfer operations. And needless to say, there's a kernel driver which gives you the ability to control, set up, and have authoritative control over the objects, and a data path that allows you to go direct and interact with the hardware, so such that, like David Ahern was saying earlier, if you really need performance, you need to get software out of the way. If you look inside that, that thing is further broken into a couple of sections. One's called the semantic layer, or the semantic subsystem, and this subsystem is responsible for all the semantic operations of a libfabric transaction. And then below that is the layer we're going to talk about more, which is the packet delivery subsystem. This is the system that provides reliable ordered, reliable unordered, and actually there's a few more, but these are the two we are focusing on right now. It does all of the buffering, the retransmission, the hacking, the knacking, the sacking, blah, 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 blah. And with that, I'm going to hand over to Nick, and he will take you through to the rest.
Hi, folks. I'm a member of a small group within the UEC that is concerned with implementing the UET specifications for the Linux kernel. As Shrijeet mentioned, we've started with the lowest layer called the packet delivery sublayer. It deals obviously with packets. It is actually the basis of the whole ultra Ethernet communication model. So it has two, well, we're focused on two modes right now. As Shrijeet mentioned, one is the reliable order delivery. That is very classic. It's in order. It expects all the packets to come in order. So there's nothing exciting there. And the reliable unordered delivery, that's where currently all the interesting and innovative new technology comes in. I will talk more about this in a moment and how we've actually designed the kernel modules and the kernel split. So we have, first, initially, we've thought about two basic kernel modules. One is the Ultra Ethernet core. As you can imagine, that deals with the generic configuration and management for Ultra Ethernet. That these are object lifecycles, resources, and so on, which are actually will be shared by all Ultra Ethernet drivers. It will provide generic interfaces for netlink, and also it will, well, in the future, it will also deal with verbs character device. We'll talk more about that later. And we have the Ultra Ethernet software device model, which is called UECon right now. That is actually the first Ultra Ethernet driver. It's entirely in software. It implements the Ultra Ethernet specifications. And since we don't have yet available Ultra Ethernet hardware, that's actually the first implementation that we're using to test communication that follows the Ultra Ethernet specs. So the software drivers, it is modeled after a Linux UDP tunnel network device. Since Ultra Ethernet is carried over UDP, mainly, it also implements congestion management, and it implements all of the Ultra Ethernet sublayers in software. And obviously, it's dependent on the core UE core code. Right now, this UECon driver is part of Ultra Ethernet. So they're not split yet in the RFC that we've sent, just because we are missing some key pieces that I will talk about in a minute. So the UECon, that's actually the interesting part. That's where all currently the magic happens. It is, as I said, a single UET driver. Right now, UE core will live in drivers Ultra ETH. That's still under discussion. It's actually one of the points that we wanted to bring up with posting the RFC. Where do people envision for that to be in the Linux kernel? Because there are different opinions, obviously. Initially, we see that as drivers Ultra ETH core, where all the core code is that will be shared by all drivers. And then we probably will move the UECon into drivers Ultra ETH, either devices or hardware. It's under discussion yet. So the UECon implements the packet delivery sublayer specification from the Ultra Ethernet communication stack. It's actually responsible for dynamically creating ephemeral packet delivery contexts. So these are called PDCs. A PDC is basically a connection between two endpoints. It's what you see as in many places later It's actually the smallest object that we work with when talking about endpoints. There can be multiple PDCs between the endpoints, obviously. So the PDS also keeps track of unique PDC IDs. These are like the DMUX. This is the DMUX information we use to identify both ends of a connection. So in addition to the standard tuple, IP address, port, and so on, we also have these IDs to identify this particular flow. So the PDS is also responsible for the packet delivery over Ethernet. As I mentioned, right now it's over UDP. There's also work to do it over IP directly. It's still under discussion. It transmits and receives NAC packets for different types of errors. So in general, there are errors that can be recovered from and fatal. Right now, we only support fatal errors, which are obvious. I mean, for example, mismatch of addresses, non-existent PDC ID on the other end, and stuff like that. So it also is responsible for, as I mentioned, demuxing and finding the right endpoint. So when a packet comes with a PDC is received, we take out the PDC ID of the destination, and we find the context that this packet belongs to. So there are different packet types. There are RUD, ROT, RUD. I will mention that just briefly. We're working with RUD and ROT mostly right now. We have ACK, NAC, and control messages for actually various events. For example, if you want to close the communication or request, or even a probe, send a probe, it's still a control message. So as I mentioned, PDCs are ephemeral, they're dynamically connected. So for example, when a host starts transmitting, it should set a SYM flag. So the other end knows if there's someone listening, it will automatically create a PDC and return an ACK. The ACK can actually return data with it as well. There's support for that. So we have a pretty quick, so to speak, handshake. The PDCs track the transmit and receive packet sequence number spaces. So we have packet sequence numbers per packet. That is used for retransmits, for tracking if we lost anything, for even ordering if ordered mode is used. So we also have support for coalescing ACK, which is, as the name suggests, we can delay an ACK so we can transmit more data. It is completely configurable right now, and we also have selective ACK for various events. So you can see that UEC is designed from the ground up to actually cover cases of which previous protocols have problems with, such as drops or reorders. Even if you use RUD unordered, it's actually ordering is not even an issue here. You can do multipath spraying to actually better utilize the links. So that is supported by the protocol from the ground up. Obviously, you can establish multiple PDCs between two endpoints, so they can more efficiently communicate. The modes are reliable ordered, reliable unordered, the ones that I mentioned we are interested in. There are also reliable unordered idempotent operations. That's a more interesting one, where obviously two of the same operations cannot change state. And we have unreliable unordered delivery that is, as the name suggests, completely packets are not tracked and unordered. So I'm going to show us a very simple flow of what we are looking at today. What's the application workflow? So we should have a privileged process that creates a UET context. That is the root object that has all of the information for that, say, communication domain in that host. It manages all the resources, and it's responsible for freeing and destroying everything once it's deleted. So first, an app has to create a UET context. Then it has to create a UET job. So we need a job ID to associate an endpoint with. So when it becomes associated, it's like a binding, like doing a bind. So they can start transmitting and receiving packets for that job. So right now, our driver also automatically creates the network tunnel device. You can see the red line over there. It's red to show that that is something that we will remove later, because as I mentioned, the tunnel device is just another UET driver that has to have its own life cycle, and it should be managed separately. So when an app wants to do any communication, it first has to open a special character device that is created for the context, which is in dev ultra ETH. It has to get associated to a job by a service name and job ID. And then it can start doing reads and writes. Right now, I'm saying reads and writes on purpose. We don't have yet queues or any zero copies, so it's just simple communication right now. Not that effective. So this is more detailed view of the same. Here, if you take a look at the RFC patches, you actually can make sense of this diagram better. It's how the code is split right now. So we have the UECon-C, which is the network device, which manages the UDP tunnel device. It has its own netlink configuration. We have the job code, which manages the job lifecycle, which means create, associate, disassociate, destroy, and so on. Obviously, we have some debugfs that is yet not sent upstream. This part, it's for our own use right now. It's just to be able to debug much easier than to with just cutting files and just seeing what's the current state without too much trouble. So where the whole magic is and where all the code actually that's interesting for retransmit, for SAC, NAC, and so on exists, that is the UET PDC. That is actually implementing the packet delivery context state machine. It also is responsible for passing the packets to congestion control contexts. We yet have not upstreamed the congestion control algorithms, but that will come as well. We have the UET context. Obviously, that is for managing the root object, as I mentioned, that is created initially and destroyed last. Then we have the UET netlink, because we have a new generic netlink family for UET that allows us to manipulate these objects. And where the PDC actually ties everything up is in the PDS code, which is the actual packet delivery sublayer. That's the whole layer. There are the entry points for receiving and transmitting packets, processing ACKs, NACs, requests, whatever. All the packet processing goes through there. So, and finally, we have the character device that is currently in the RFCs tagged as a hack patch, because it's obviously, we don't intend to continue with that for the future. We just made it to be able to actually test the PDS more easily and to be able to link it with libfabric so it can do some communication, basic communication. So here's the UET code organization. It's what it is there today. We have everything together under drivers ultra ETH. Everything means UET core and UECon together. As of today, the PDS is part of the context, which will move to UECon once it becomes its own driver. As I mentioned, the network device is created dynamically right now with contexts. Again, that will change. It will be created on demand only when that driver is actually used. And the custom character device that will be removed later and probably replaced by a special UET IB verbs device that's still under discussion. We have a new kernel config option for Ultra Ethernet. It's obviously config Ultra ETH. And we have the Netlink API for UET core resource management. As I mentioned, that these are the common resources that will be shared by all UET drivers. So where do we see this going from this state for the next posting? UET core will move into its own directory and its own kernel config option. The device drivers, of which right now UECon is the only one, will move into their own directory and again their own kernel modules. The congestion management and additional UET layers will be also sent. We actually need those for proper communication. Right now, those are missing, so we only have like the lowest layer of UET that is responsible for the packet delivery, retransmission, and so we also miss the UET core to UET device in kernel API right now, which is needed to actually split these parts. So this is basically where, when an object is programmed in UET core, we need to obviously program it into the device drivers. So we will have that API ready as well for the next posting. And the last one is actually the most controversial one. We are still in the process of specifying the UET core to user space API, which is yet to see how it will go, because we need to actually design this API with other RDMA, well, not design, but fit that API with other RDMA users. So, outstanding actions. We're always happy to have more people involved. We're right now a small group. There's like a person per piece right now to work, but we would like to have more hands on deck, obviously. We would like to leverage the RDMA layers. We're working on that. There are a lot of pieces of RDMA currently that are reusable. We don't want to reinvent the wheel, obviously. We want to reuse it. And yeah, as I said, there are patches being prepared for that. Also, user and hardware interfaces are right now mapped as libfabric, as also Shrijeet mentioned, which makes testing difficult. We'll have to work on alternative ways to do that. And actually, there are in-kernel implementations that would like to use the PDS layer, such as storage. They're looking into how they can leverage the code that we're working on to use that for storage purposes. Yep, that's all. Any questions?
Hello. I got a little lost on what you describe as context versus jobs versus the resources.
Yep.
What is the hierarchy?
So in terms of hierarchy, you'll see the context is the root object, which actually everything starts from that and is contained in it. So all the generic objects are inside the context. There's a job registry inside the context. So if you create a job, you have to first have a context. You create the job inside that context into that job registry. A Fabric endpoint can associate with that job and start communicating.
Okay, so there is one endpoint per context, or it could be multiple
endpoints? The endpoints are not limited. So right now we have an artificial limit of one endpoint per job, but we will extend that to support multiple endpoint associations with the same job.
So you have contexts at the top layer.
Yep.
Each context has a job, one or more jobs.
Yes.
Which has one more endpoints.
Yes, exactly. Yes, yes. Thank you.
Hi, folks, can you hear me?
Yeah, we can see you, we can hear you, so you're on.
Let me just share my screen. All right. Thanks for the invite, Shrijeet. All right, so this is roughly a rerun of the talk we did at Hotnets last year. This is based on a research paper my team and I at the Polytechnic of Bucharest have published last year. And this paper looks at, what might you build if you had a lot of money and you wanted to outcompete OpenAI and such companies. So this is some news that probably was also last year, where there were these public plans that Microsoft and OpenAI were building, 100 billion data center. And this is, I think, came out just a year ago. And since then, we've heard, many more stories like this. X is doing the same, and other companies, there was like this 500 billion thing, and then, So the question is, okay, if you had this type of money, what would you build and how hard would it be? And we asked this question from a networking point of view, but to get to the networking side, we had to sort of understand the other aspects of building this thing. So to put things in context, a large supercomputer such as Frontier has around 40K GPUs today. X and Meta's training clusters are around 100K GPUs. And based on the budget of 100 billion and doing lots of back of the envelope calculations, we basically came to the conclusion that you could buy just under 2 million of NVIDIA GPUs, since the plan is to build these things sort of in the future. You'd buy the best available GPU, which currently seems to be B200, assuming you can actually get it. So, okay, so in terms of power consumption, current data centers involving GPUs, they're like, on the tens to hundreds of megawatts in terms of power. Now, if you do the maths for this one, it's actually, more than an order of magnitude larger. It's like 5 gigawatts, which is quite something. So, I mean, for those of you that don't know how much 5 gigawatts is, for instance, Romania, which is an entire country, the average power consumption, if you take like the peak during the day, is around 5 gigawatts. So it's basically like a, medium-sized country. It's a lot of power. So, okay, so then that's great. Surely there are places where you could place this in the US. And, what my team did, they looked at all the power grids in the US, and they looked at the historical data for those power grids, and they saw, how much power has been generated, and they took the max, and then they took the maximum consumption for those networks, and basically they tried to see a difference, to see how much power you had available. And the answer is, well, there's no single grid where you have this much power, and you'll have to really break the data center up. So as Shrijeet said, the reason you would build such a big data center would be to have it act like a single sort of big computer that does training in lockstep. But there's the sort of slight issue that you will not be able to build it in the same location, so you'll have to split it up. Now, if you split it up, the best way to split it up would be to split it up east-west, because you have customers on both sides. You'll be using this data center not only for training, which would be sort of the first part, but also for inference. And for inference, it really makes sense to be close to your customers. So probably you're looking at the east-west split. And yeah, so that means for training, you'll have something like 20, 30 millisecond RTT one way. No, 30 millisecond sort of one-way delay between the data centers, which is quite a lot. So, and these just sort of complicate the design of what you have to build. So takeaway, these are public plans by a company. We just went and looked and, what does it mean? And it basically means you have to build distributed data centers. A single data center to have this many GPUs, you just can't build it. There's not enough power. There's probably a lot more constraints, but even at this basic level of having power, you just, it's not possible. Okay, so next step is, what could you build, right? So this is a famous scaling curve that was published a while back. And, we've had the papers like this coming also from Google, but also from OpenAI. And basically what this says is, look, if you have more compute power, then the best way to use that compute power to create a better model is to actually increase the size of the model, right? And this is the reason why these big companies have been betting the farm on building larger and larger data centers, because the assumption is that bigger is better, and the company that gets the biggest model wins. That's basically the assumption. So for reference, this is GPT-4 is around 2 trillion parameters. What we basically did and looked at the amount of compute we'll have available in this future data center, and we said, okay, why don't we go crazy and say take something like a 100 trillion parameter model? That seems to be like 2 orders of magnitude larger than what you have today, which is ambitious enough given the amount of investment. But of course, you could go for a 50T model instead of a 100T, whatever. Like a lot of the calculations we did are more or less the same. So what we then did is said, okay, if you wanted to build this model, how big would the model be? And then you can derive from sort of the literature how many layers this thing needs, and basically, if you want to just load the layer into the GPU's memory, it turns out you need 18 B200 GPUs just to hold one layer. So this will have to be like massively distributed for it to work. Okay. So how do you train this? So Shrijeet did a very good job of sort of presenting the big picture. I'll go over it again. So if you look at a B72 rack, like this is in the literature, this is called a node. So basically, you've got a compute unit that has a CPU inside and a bunch of GPUs. Initially, the number of GPUs inside the node used to be fairly small. Like today, you have like 8 H100s in a box. There is a trend to put more GPUs in the same box. So the NVL72 packaging gives you 72 GPUs in the same box, and it comes like a rack. So if we assume this packaging NVL72, basically you've got 72 GPUs that I'm sort of clumsily showing here, and they are connected between them with a in-rack network called a scale-up network that's very, very fast. So this thing is like 14 terabits per GPU. But also each GPU has an RDMA NIC that connects to the scale-out network, and this is 800 gig for the B200. So obviously the scale-out network is much larger in size. It connects the entire data center, whereas the scale-up network is really just for the rack, but it's much higher bandwidth, like 16 times more faster than the scale-out network. Okay, so given this, you've got this humongous model. How do you split it up across your data center to train it in the most efficient way? And basically, I've already said that you need 18 GPUs to hold one layer, and you've got 72 GPUs, so you'll have 4 copies of a layer inside the same rack. You could go for having the same, having different layers in the same rack, or having the same layer, just different copies of it. And this brings us to, how do you train distributedly? There's like multiple techniques people use, but the most basic one is to have different copies of the model data. You split it in half. Half of it goes into the left, half of it goes into the right, and then you somehow synchronize the models periodically. And this is called data parallel. Basically, it turns out that for data parallel, there's a lot of communication that takes place, and what you really want is put copies of the same layer inside the same rack. So you will have 4 copies of layer 1. Okay. Obviously, this model has like hundreds of layers, so you'll need 134 racks in total to just hold 1 copy of the entire model. Okay. So layer 1 is in rack 1, layer 2 is in rack 2, and so forth. And to do the training, basically, you have to start plugging in data from here, and they will sort of trickle down all the way to layer 134, and they're going to come back. Okay. And this is just 1 copy of the model, but of course, you have a lot more copies because there's a lot of racks. And then you'll have 2 data centers that you've split this in. We assume an equal split. Okay, so what we're looking at is we have like hundreds of model replicas per DC, and you have 2 data centers. Okay. So that's basically how you'll split this thing up. And if you're really curious to understand the details, you can have a look at our paper, and that sort of describes, all the reasoning behind this. But this is just a sort of a crash course on how you might do this. By the way, we don't have any insights into what OpenAI is doing. This is based on published information on best practices in the network and published data about what they're planning to build in terms of how much money they're willing to spend. Okay. So how do you do the training, right? So basically, you've got some input. You have, a huge data set, some crawl of the internet, and you break it up into small pieces called mini batches, and you take this in and you put it through layer one. Basically, it goes into one of your racks. And what I'm showing here with this magenta color is the scale up communication that happens during this forward pass within the rack. Okay, and as Shrijeet was saying, this is basically reduce, scatter, and all gather. I'm not going to go into details, but basically, after you do the computation within the rack for the sort of split layer you have in your rack, then the outputs of this, they have to go to layer two. And here you're using the scale out network. So, you have to come out of your rack, go via the scale out network, go to the next rack, and so forth until you've reached the last layer. And at this point, you have a sort of proposed output for this input, right? Now, of course, when you start off the training, all the weights of the model are completely random. So, this Y will not be particularly good. So what you have to do is to basically plug it back in and compute how far it is from what you'd like to see, which is basically what the initial text looks like. You've given it a prefix and you're looking at what is the suffix. Does the suffix match or not? So then there's this backward pass where basically you're taking the outputs and you're plugging them in the model all the way back. And again, you have some scale out communication and then quite a bit of scale up communication. Okay. Now, what is interesting is that because you have many replicas of this model, when you're doing this backward path for each layer, you'll have to synchronize its gradients with all the other replicas. Remember, we had hundreds of replicas. So in this pass here, we have to talk to 300 other replicas somehow, and basically tell them what our weights are, and we do a sum of sort of all the weights, and some averaging happens, and basically everybody gets the same result. And this is this all reduced in here. That is quite it has to carry quite a lot of data. And the question is, well, there seems to be a lot of networking here just by eyeballing the whole thing. How much does this cost? So in terms of how much the GPUs are busy, our estimations are that for both forward and backward path, it takes around 400 milliseconds of GPU compute. Actually, the forward takes 130 and the backward takes 260 milliseconds. And the communication, just out of this entire thing, 20 milliseconds of communication is not masked by compute. Actually, this is the biggest metric we care about. How much communication do we have that is not masked by compute? Because if it's masked by compute, it doesn't mean we're waiting for the GPUs anyway. It doesn't matter that we're waiting for the network too, right? But the problem is the GPUs are so expensive, we don't want them to be idle waiting for the network. So exposed networking is really what we care about. Okay, so if you look at our estimation, assuming a perfect network, just looking at the headline speeds and so forth, we estimate that with the provision capacity for the B200, you're looking at 5% exposed communication. Now, if you have another architecture of a model, this becomes more like 20%. And again, these are just ballpark numbers. This is just assuming everything is perfect. Okay. Okay. Obviously, in practice, everything is not going to be perfect, but that's a different story. Okay. So the takeaway here is that we really need to be careful with communication, because if this exposed communication becomes a problem, then your GPUs are basically idle waiting for the network, and then everything crumbles. This distributed training becomes infeasible all of a sudden. Okay, so the biggest question is, well, we've taken a point, which is the B200, which says we have 800 gigabits of scale out and 14 terabits of scale up per GPU. How did they arrive at that number? What would you do if you had different speeds? And this graph looks at exposed communication if you have more or less capacity for scale up per GPU, right? So the current point is this one. So this is what NVIDIA has provisioned, and obviously other vendors, they have similar numbers. Now, if you put less scale-up bandwidth, like 3.6, all of a sudden networking becomes more and more exposed because there's a lot of stuff happening within a node. And then, obviously, if you don't have any scale-up, you just rely on the scale-out network, then you're looking at like spending between 50 to 80% of your time waiting for the network. Obviously, this is not something that you want to do or feasible. So this graph sort of explains why people build such high performance scale-up networks that are, many times faster than the scale-out networks. And the reason is because they're actually helping quite a lot minimize the exposed time. Okay. Now, if you look at the scale-out speed, so what is my RDMA NIC speed connecting to the data center network? The answer is, well, this is the current point we have today. And it's more or less okay. If you go to higher speeds, it does seem like mixture of experts models will be behaving quite well. However, for basic transformers, by the way, basic transformer is what Llama is. So Llama from Meta is a basic transformer. OpenAI is building sort of an MOE model, and DeepSeek is also MOE. So depends on exactly what you're doing. But basically, if you're building a standard transformer, it looks like 400 gig of scale out should be sufficient. It's not a bottleneck. You see, you reduce the speed and the exposed communication time does not increase, so that's good. But if you're doing MOE, probably you need even more bandwidth. Okay. So obviously, this is done with a lot of caveats, but that's the idea. And again, here we're assuming the network is perfect. Okay. Okay. So how do you build this network? Well, before we build it, we have to understand what the traffic patterns look like, right? So let's look at this thing called pipeline parallelism, right? So basically you have racks here. And what I'm showing here is one replica of layer 1 in rack 1, one replica of layer 2 in rack 2, and so forth, okay? So basically what's happening is you have the inputs coming, some training text comes in, and then these guys, they basically compute some output. And if you look at the size of this output, it's around 4 gigabytes, okay? So what you want to do is to basically send these Ys here to the second rack. And logically, the simplest thing to do is every GPU from the first rack copies the entire Y data to the second rack. And by the way, it's the same Y, right? Everybody has the same output, sort of same input needs to go to their correspondent GPUs in the next rack. Problem is, this is actually quite big. So 4 gigabytes at 800 gig gives you like almost 40 milliseconds of exposed networking. So that's a lot. Okay, so to avoid this, what you really want is to basically break up this data into 18 shards because it's the same. And then everyone copies their shard to the remote guy. It's like just point-to-point communication. And then there's an all gather happening at the destination where everybody, over the very fast scale-up network, everybody gets the data. And if you do this, then you can do this in like 2 milliseconds as opposed to 38. Okay. So basically, the takeaway here is that even for obviously simple traffic patterns, we might use both the scale-up and the scale-out to make sure we don't increase the exposed networking time. And what is interesting from the scale-out network point of view, this looks like a point-to-point traffic that is, all of a sudden loading the network to the max. If you look at the entire rack, just last 2 milliseconds, then it stops. Okay. So let's take another look at of a primitive. This is this synchronization of gradients that I was mentioning. This is called all reduce. So the standard way you implement this is by doing a ring or reduce, like Shrijeet was showing, right? So you've got your 4 replicas within the rack, and then there's like hundreds of replicas across the data centers and also in the remote data center. So the simplest thing you could do is to do this thing called ring or reduce, where you create a ring that goes across the scale-out network. The problem is, if you compute how much this would take, look at the size of the data, this will take something like 7 seconds. And remember, our budget was around 250 milliseconds. So 7 seconds is clearly out. We have to do something much better. So then what again, but look at, if this hierarchical reduce has the nice property that very few flows are leaving the rack, right? You have just one flow going out and one flow coming in. This looks like nice from a network point of view, but it's actually bad from a completion point of view. What you end up doing is, again, using this scale-up network and its power. So the first thing you do is you basically reduce within a rack. So everybody gets the same data within their own rack, okay? And let's assume for now that this is instantaneous. If you do the math, this takes like 60 milliseconds, right? Then you have 18 parallel all reduce rings happening between each GPU with the same rank. So GPU 0 will be in all reduce ring with GPU 0 from here and from other racks and so forth. So you've got these 18 all reduce rings happening at the same time, which basically means that the amount of data you need to carry across the scale out network is this thing divided by 18, right? And this just takes less than 100 milliseconds. And after you've done this, then you have to do an all gather to get the final results within the rack, and you're done. Now you'd think that you need to add these things up, like 16 plus 98 plus 8. In practice, you don't, because what you do is you chunk up the data and you work per chunk. And because of this pipelining, you'll basically be going at the speed of the slowest resource, which is in this case the scale out network. So the end result will be something like 100 milliseconds. And again, from the point of view of the network, this will look like all of a sudden, all the GPUs start sending at the same time, each of them talking to another GPU in another rack. They go line rate 100 milliseconds, then they stop, okay? Okay. Now, okay, so I've told you what the theory is. So what I've shown there is, a logical view of the network. These things start, they go at line rate, they stop, right? But how do you build a network to enable them to go at line rate so that, some of them don't get like half of line rate or a quarter of line rate or whatever? So, this is basically what you're trying to build. You've got 10K racks and you have 800 gig links, right? So the theory is very simple. All of these big cloud companies, they've built multi-tier clone networks with 4 or 5 tiers or whatever, where everybody talks to everybody, and you have enough capacity. Well, it turns out that if you try to do the same for ML networks, this is very, very expensive. So basically, the maximum number of nodes you support in a flow is related to the switch radix and the number of tiers you have. Okay, so the largest switch we have in production today is a 51T switch, which can be configured as 64 port times 800. This means you need 4 tiers to connect 800 KGPUs, which is our target. And if you do the math, actually, this is crazy expensive, right? Even just the cables themselves cost billions, because the cables are very expensive. They have these transceivers. Each transceiver costs like whatever, hundreds of dollars. So you end up paying a lot, right? So remember this number, 70K switches. This is a lot. Okay, so what can we do to reduce the cost? And this is not a hypothetical question. These things are already happening. People are applying these very simple optimizations to reduce the costs, but this makes the network peculiar. It's different from a cloud network. Okay, the first thing is this observation that, well, wouldn't it be nice if we had higher radix switches, right? So I said we have the largest switch we have today is 64 times 800, okay? But, well, what if we did, what if we did a switch that is, say, what was it? So the same 51T switch can be configured as 256 200 gigabit ports, right? So the product is the same. 256 times 200 is 51T. You could do 128 ports of 400, okay? So this is what people do. They say, okay, we'll now build switches, but inside each switch, we'll have multiple chips, multiple switching chips, each of them with 51T. And, oh, no. I'm getting I've started talking about this slide. Sorry about that. Okay, so I will put multiple switch chips inside a box. And what is nice is that now the radix of this thing is higher. Okay, so I have 256 ports. I will need I will need fewer tiers to connect the same number of hosts, which is obviously great. But you will ask, well, now you only get 200 gigabits per GPU, which is not the same as before. So why is this a good thing? Well, this is why, because basically what you're doing is you're putting 4 chips within the same box, and you're using a single wire to connect the GPU to the box, right? So on a single optic fiber, you can basically carry multiple lambdas, and each of these lambda will be 200 gig. So you have a single transceiver here, single transceiver here. Still, you pay for a single wire, but within the switch, when you go from optics to electrics, you'll basically have 4 copper backplanes going to the different chips, right? So now, logically, you've got 4 different networks that are completely independent, and these are called planes. Okay. So if you do the planes, then basically you can actually get away with much fewer planes. But obviously the challenge with the planes is that, well, debugging what happens and so forth is much harder. And now if a GPU wants to go at 800 gig, it has to somehow spread the traffic across these planes. Okay, and let me go back to this. This is what Shrijeet was saying. Basically, because each GPU talks only to its correspondent in the other racks, you don't need to connect everybody to everybody. So what you could do is connect only GPU 0 in a network of their own and call this, rail 1. And then these GPUs, the brown GPUs, will be in their own network. This is rail 2, this is rail 3. So what I'm drawing here is completely independent networks that are not connected to each other. Okay. There's also an alternative where you connect them sort of at this tier, and this is what Shrijeet was showing. So there's different ways in which you can do this, but basically by reducing the number of GPUs you connect to, you can actually reduce the number of tiers quite a bit. And this is what people are reportedly building. So if you look at literature from like hyperscalers, they will say we're building multi-rail, we're building multi-plane. Okay, done this one. Okay, so sort of nearing the end of my my talk. So is the current transport we have good enough, right? And basically what we have today is RDMA, which can be either over Ethernet, in this case it's called RoCE, or over InfiniBand. In both cases, the speeds are more or less the same. And what I'm showing here is just the pipeline parallelism phase that I was showing earlier. So, rack 1 sends to rack 2 the outputs of layer 1 going into the inputs of layer 2. And what you have is literally just everybody doing this at the same time over a fully provisioned scale-out network. And the network is provisioned such that everyone should finish at 1 millisecond. But what we see here is that actually some flows take as much as 9 milliseconds to finish. And the reasons for this are basically twofold. First of all, you get these collisions because of equal cost multipass. So when the switch spreads the traffic, it will randomly select a port per connection. And this choice can be quite bad. And the other problem is this thing called PFC, where there's a lot of collisions, switches run out of buffer, and then they back pressure and they stop their correspondent switches. So this looks really bad. So obviously RoCE is not a good solution. If you just get rid of RoCE and use like a state-of-the-art single path congestion control protocol, you get rid of some of the issues. So this, the tail of this was mostly due to PFC, but still you see that this is quite bad. So what you really need is something that spreads the traffic across the available paths, and you get this by basically using multiple paths. So if you use 2 paths per connection, this is what you get: 8, 32, and then 128. And basically, what the UEC transport does is exactly this. For a single connection, it spreads the traffic across all of the available paths and allows you to get this. And this is crucial not only because you have this synchronized on-off traffic pattern where everybody starts at the same time, they want to finish at the same time and fully utilize the network, but also because you have multi-plane and really you have to somehow split the load across all of the available planes. Okay. So this is just my sort of summary slide that things are changing dramatically in the networking landscape because of AI/ML. And I guess, this being Linux, you guys understand this part, TCP/IP and sort of software-based transports. The scales of modern cloud networks were also very, very, very large, hundreds of K, maybe millions, but any single job maybe did not exceed more than 10K, and you have quite a few flows per host, right? So you have a lot of stat maxing and also a lot of parallelism such that the kernel could do the job of the transport. In contrast, the job scale is really the data center scale in AI/ML, which is the big difference. You have very few flows per host, active flows, maybe just a couple, and they go at directly line rate, right? So which makes everything harder, like load balancing, congestion control, everything else is quite hard. And that's why, there's quite a bit of work also in standardizing switch support to help these transports behave better and so forth. So that's all I had. I'm not sure whether I completely bored everyone or this was interesting, but anyway, it's difficult to tell when you're remote because I cannot see the room. Yeah, any questions?
Yeah, Costin, no one left. So there.
Excellent. Did anybody sleep? Fall asleep?
Here's a question too.
I actually have two questions. The first one is to the previous slide, where you're showing the scaling depending on the number of paths. So in this simulation, did you assume any congestions on those paths, or just scaling them up, like having them more of them?
So hold on. So this is okay. So this is the same network, fully provisioned network. This is an 8K leaf spine network, and you have exactly 8K flows. Just this pipeline parallelism. Everybody's doing, sending from their layer to the next layer, right? Everybody's finished at the same time, and they're going next. And now the question is, when they're sending, they're all trying to send the same amount of data. And what you really care about is when the last one finishes. So if you use something like standard Rocky with a single path, like you do a single RDMA write, for instance, for that flow and wait for it to finish, this is what you would get. You would get this one, like there'll be a poor flow that finishes at 9 milliseconds, where you have some lucky flows that finish at 1 millisecond, and then depending on how many collisions they have, they will take a long time. With multipath, it's the same sort of API to the application. The application still does a single write, but the transport underneath basically changes the entropy in the packets. It cycles through 128 entropies, like 128 UDP source ports, right? And then when the switch selects one of its uplinks based on the 5 tuple, it will select a random uplink, well, not random, but it will basically spread traffic much more evenly across all of its uplinks, and that's why you get this behavior. And of course, the end host transport protocol, does load balancing of its own. In the case where there are still some small imbalances, it will actually push traffic away from congested paths onto uncongested paths. Does that answer your question?
Yeah. And another question, because you started from spread geographically data centers, did the calculations along the presentation also include the delay between east and west geographically?
Yeah. So basically, I didn't include them in the talk. The analysis is in the paper. So basically, in this hierarchical, so across the data centers, again, you will do this hierarchical or reduce. And it turns out that you can also do it without being blocking. So you can mask the inter-data center delay. And the way you do that is by basically sharding this communication across all of your GPUs, right, in your data center. So after you've done the local or reduce in one data center, everybody copies a small pixel across to the other guys. And really what you want, in terms of wide area bandwidth, I think 20, 30 gigabits per second was sufficient to do this thing, right? So per GPU. So
Yeah,
the GPU had like, you know, this 14 tera scale up, 800 gig scale out within the same data center, but then across, you know, just 20 gig was enough.
Yeah, this is okay, but what I mean is there is a delay because the speed of light is finite. So the delay between data centers across two sides of USA is, I don't remember, 20, 25
Yeah, something like that. Yeah. So yeah, exactly. So you can mask that delay. Basically, you know, the 20 milliseconds can be masked. You have enough slack such that you don't you will not delay the computation, basically.
Okay.
Thank you. Yeah, the important part is the relative completion time, right? It doesn't actually matter what the absolute, well, I mean, it matters, but the absolute doesn't matter. And in that, like Costin was saying, whether you're going data parallel, pipeline parallel, or any other kind of parallel defines whether it'll affect your outcome or whether you will just be able to pipeline that away and mask it, like you were saying, right? So there's a lot of complexity behind these, right? None of these are simple, and none of the systems are, oh yeah, I pulled out a blueprint, I built it, wrote a big check, which you may know something about, and then be done. Okay, yeah.
Hi, Costin. This is Stefano. It's a pity that you are not here. Anyway.
Hey, Stefano. I wanted to come. It just was not possible this time around.
Okay, don't worry. So I just want to ask, so you mentioned this solution with the spraying, but I just want to ask if you could allocate your flows in the best way among the possible paths. Do you think that it will be possible to avoid congestions, or do you think that it is not possible, this one?
So people have tried this, and by the way, a lot of the systems being deployed today are still based on single path Rocky. Like there's no good multipath solution in deployment today, as far as we know.
That's not exactly right. There is a
maybe Shrijeet knows, but
no, so
anyways.
I think I would say it this way, right? I think the answer I would give is that the most common deployed design is what I was showing as the rail optimized design, where effectively you've taken the congestion out and you let your CCL do the coordination and the scheduling for you. So you minimize conflict. But
yeah, if you have a single switch, it doesn't matter. So if you fit within this rail optimized thing and you know all your traffic is within a single switch, then there is no problem with multipath. That is completely correct. You could, I mean, Meta has this paper on training Llama, and they explain what they did. Basically, they try to, for instance, based on the destination of where you're going, you're trying to select a spine and do some sort of source routing. So you could do that, and people have tried it. And it works really well until you get one failure when you switch back to ECMP, and then you basically lose half of the capacity. And the problem is in these large networks, you always have some failures, right? It's, you know, you start off well, but then this thing has to go on for like 3 months. And you know, every time there's a failure, you have to keep going because you're not going to stop everything until you send the engineer to fix. So the answer is, well, it's in practice, it's very hard to make these things work. And this is this, I think it's a SICOM 23 or 24 paper from Meta that explains this stuff. What people are doing to sort of mimic or to simulate multipathing is they're using this thing called QP scaling with standard Rocky, where instead of using a single QP between two pairs of endpoints, you use N, like you use 8 QPs or something, right? And basically what this does is this is like a sort of a version of multipath. We're using, you know, fewer flows, but it does help. Like if you look at 8 paths, right? So with this solution, it does, you know, cut the FCT by quite a lot. Now, with the software solution of QP scaling, you don't actually get these benefits. It's probably a bit worse, but it's still much better than going fully single path. Now, QP scaling comes with other issues like, all of these NICs, they are optimized to have a small number of QP. It's a small QP cache, right? So whatever fits on chip in SRAM is, typically a fraction of the total QPs that you may have. And, the more QPs you use for a single connection, then this creates pressure on this cache. So if you overdo it with the QP cache, then it may work well for 1 or 2 connections. As soon as you have like 5 active connections, all of a sudden everything comes crashing down. So there's a lot of trade-offs happening here, and people are fighting this war right now.
I have to add, not all NICs have that problem.
Of course, no. This is like in general. Obviously, some NICs have more capacity, more SRAM, and maybe the problem does not appear for, particular workloads. But in general, there's limited hardware resources, and I mean, there's a lot of research literature on this. If you're curious, Stefano, I can sort of point you to it.
Sure, thank you.
Any more questions? People are ready to go home. I think everybody's checking their bus schedule home. All right, well, in that case, thank you. This was an exciting first day. Where's Jamal? Oh, there he is. Any final, do we have to say anything tomorrow, 9 o'clock? Be here or be square? Thank you.
Thanks for the invite, guys.
Thank you, Costin.